Hi everyone, we're going to look at some mathematical induction questions that involve sigma notation, and let's recall what we might already know about sigma notation. Now when we're talking about sigma, we're talking about uppercase sigma, the Greek letter, which looks kind of like that. Okay, it's not this one here. Okay, that one's used for other things, for example standard deviation in statistics. That's got nothing to do with this video. Alright, it's for a different video, but we are talking about sigma notation, which uses uppercase sigma, and you might find that this sigma symbol often has some numbers above and below, and it might have something like a definite number or an indefinite number. So 5, you might have something like I equals 1. And we might have something that involves I there, like that, and that would create a sum. Alright, now the sigma character pretty much means summation, so add this together is kind of what it's saying to you. So for this one here, write the sum from I equals 1 to I equals 5 for 2 to the power I in expanded form and evaluate. We'd simply write it as such. So that basically means I starts at 1 and this I parameter here is changing. So we would sum together 2 to the 1 plus 2 squared plus 2 cubed. You get the idea, 2 to the power 4 ending at 2 to the power 5, and we get 62. So that's evaluated as 62. So how do we use this in induction? Here's an example. So we have to prove that r equals 1 through to r equals n for 3 times r equals 3 by 1 plus n all over 2. Rightio, so we go through the same steps of induction. We do need to conceive in our heads what that left hand side of the equal sign there looks like. Okay, now we might think, what does that look like? So in our mind's eye we're thinking that is simply just the sum, and we've got 3 times 1 plus 3 times 2, which is 6, plus so on, and that would go up to the last one, which is n. Now this, because this is inductive proof, that's, of course, we do have an n there, don't we? So we've got blah 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 ellipsis points and plus n. Alright, my thought bubble was too small. Alright, so that's the ellipsis points in there. Doesn't come out too well. How's that? That's a bit better. And look, don't get r and n, r versus n, don't get them confused. Okay, so the r is just representing each of the individual values that get summed together, a way of indexing them, whereas the n is our term that we are familiar with from induction, inductive proofs. And on that note, let's start, well, when n equals 1, so the initial step, n equals 1, and we'll have our left hand side. Okay, so that will simply just be 3 times 1, which is 3. The right hand side will be 3 by 1 times 2 all over 2, which also equals 3. So it's true for n equals 1. Alright, that's a good start. So assuming it's true for n equals k, our inductive hypothesis, we would have this expression here. And of course, we need to use our inductive step now to show that if it is true for n equals k, it's always true for n equals k plus 1. So for n equals k plus 1, there are a couple of ways we look at this, couple of different angles we look at it. So basically, by substitution, it should equal the following. Alright, so we know by substitution, just following the pattern, that it should be r equals 1 to k plus 1 for 3r, and then we go by substitution, and so it's 3 times k plus 1, and the next one will be k plus 2, subbing in k plus 1 up there. Okay, and that's close brackets and all over 2. So in a sense we're requiring ourselves to prove that, and we got that simply by substitution. So considering the inductive term now, so we're going to employ the inductive term. We also know that from r equals 1 to k plus 1 for 3r, we have the sum as it is up to k plus the inductive term. And the inductive term will simply be 3 outside of k plus 1. And from previous steps, i.e. just back here, right there, we put that known result in for the sum when you go up to n equals k, and we found that was 3k outside of 1 plus k, or over 2. Adding in that inductive term on the right hand side, we need a common denominator, and we are looking at 2 for our common denominator, and we get, and just going to place this up there, so that's 3k 1 plus k plus, now we've got to multiply it by 2, this term here. Alright, we've got to multiply that by 2, and it's already multiplied by 3, so it's going to be 6 outside of k plus 1. We expand, so we've got 3k plus 3k squared plus 6k plus 6 all over 2, which can be written as 3 outside of k squared plus 3k plus 2 over 2, or if you like, 3 outside of k plus 1, k plus 2, factorised. Your choice whether you want to write it factorised or expanded. I'm keeping it factorised because it matches the result just above there. So remember, we were required to prove that, and we did. So basically we've shown that when we assume n equals k is true, then it's also true for n equals k plus 1, and also n equals 1 is true so by mathematical induction it's proven, and that's that one. Alright, so we've looked at sort of a mid-level one. Let's look at a more difficult one. Okay, now this one is a good use of sigma notation because it makes the writing very economical. So it's an very efficient notation for ones like this. Okay, so let's go back to our base case, or our initial step. Alright, let n equals 1, the first natural number, and the left hand side equals 1. And the right hand side, if you sub that in, that equals 1. So it's true for n equals 1. Okay, so we assume for some value of k, assume true for n equals k. And that would yield from r equals 1 to k for 2r. Notice how I'm not subbing in k there for the r stays as r on the left hand side, but on the right hand side for n, subbing in k now. See that? As I said earlier, don't get your r's and your n's and your k's mixed up. Now, if we consider by substitution, we should get the following result. So we're kind of trying to prove the result of this step here. Okay, so by substitution, it's clear that from r equals 1 to r equals k plus 1 for 2r take 1 all cubed, we should get k plus 1 all squared times 2 by k plus 1 all squared minus 1, and perfect square expansion on the first part of the product there, and expanding the second term in the product. Now, I reckon it's probably a good idea, looking at the nature of these things here, these two parts of the product, that expanding might be a good idea. So I'm going to ride that hunch. So expanding that and then collecting like terms, we get that there. So we're required to prove that that's what it should be based on the given expression. Okay, so for n equals k plus 1, again, we have this, and by adding the inductive term on, we get what we had, the sum at r equals k. Oh, that should be a 1. That's a 1. The 3 is there. And we add the inductive term on. Alright, so remember, this was our, every term is in that form, 2r take 1 all cubed. So it would be 2 outside of k plus 1 take 1 all cubed. Now we have a result for this part here. Okay, before we found that it was k squared outside of 2, k squared take 1. So write that in. Add in the inductive term. And now we use some of our algebra magic here. Expanding. Now we have a binomial expansion. Okay, you should know that these. Okay, so it's a cubed plus 3a squared b plus 3ab squared plus b cubed for when n equals 3. We expand out and then we simplify. 2k to the power 4. We've got 8k cubed. We have 11k squared. We have 6k. And we have 1. And you can see back up here that that's what we got. 2k to the power 4 plus 8k cubed plus 11k. Sorry, that should be a plus there. Alright. Put the wrong sign down. Plus 11k squared plus 6k plus 1. And so we conclude in the same way. So since true, as long as you talk about the three things, since true for, whoops, repeated word, for n equals 1, and when n equals k, also true for n equals k plus 1, proven by mathematical induction. Happy, happy, joy, joy.